So far, we've talked about some basics of data mining. So basically, what a database is. Especially, we talk about the Hadoop database, where things are designed for hosting big, large amount of data. And then we talk about Apache Spark and some data mining techniques in order to produce information that could be used for analytics. So now we're kind of ready to jump into the topics of machine learning and then actually apply them to a large amount of data. So the first topic of that journey is going to be supervised learning. So we're going to begin with some assignments. So this is something that I want you to work as a group. Okay. Um, there are a total of 7 questions, and um, I'm going to give you about 10 minutes to work on these questions. Before to do that, I'll explain briefly in terms of what this assignment is about. So we're going to consider 2 matrices. So we are actually going to talk about matrix algebra. Okay. Um, so let's say we have a matrix A and a matrix B, and let's say you are interested in computing A times B, right? And that's a matrix multiplication. And there are certain conditions that matrix A and matrix B needs to satisfy in order to be able to compute A times B. And I think this is pretty obvious for many of you. And then this is kind of an important question. Now, the condition for multiplication of a matrix A with matrix B. Now, when you do that operation, how many times, okay, do you need to compute multiplication of real numbers? So you have a matrix A and matrix B, and then matrix A is going to be something by something, and then matrix B is going to be something by something. Then as we multiply the numbers, right? As we multiply the matrices, we will need to multiply numbers, right? Now, the second question basically asks, how many number of multiplications do you need to perform in order to compute A times B? Okay, so you will perhaps want to kind of manually count with some simple examples, maybe 2 by 3 times 3 by 2 or something, and then try to generalize that to some arbitrary dimensional matrices. Then the question number 3 is about what is called the Gauss-Jordan elimination. For those of you who are not so familiar with what Gauss-Jordan elimination is, this is one of the simplest algorithms for computing inverse of a matrix. Okay, so for those of you who are not familiar with Gauss-Jordan elimination, there's a nice explanation on the Wikipedia. Um, and I encourage you guys to take a look at it. And there is actually an information out there you can easily search in terms of how many operations are required in order to compute Gauss-Jordan elimination. Okay, so when this course was provided under a classroom, physically, face-to-face, I used to explain some basics of Gauss-Jordan elimination, but considering the current format of course delivery, I guess we don't have room to do that. But I believe the information is not too difficult to find, so I'll let you guys figure out. Okay. Now, all of this kind of boils down to this questions number 4 and 5. Okay. Basically, when you have a linear equation, y equals to xa, where the unknown is a, okay, x and y are the objects that we already know, and a is the unknown. And then the solution for that equation is known as a equals to, it's a little, messy, but basically X transpose X inverse times X transpose time Y. Okay, so that's the solution that is known to this equation over here. Now, in order to compute A, okay, how many number of operations do we need to perform, right? And the hint here is that from the question number 2, we have already talked about how many number of multiplication we need to do in order to compute A times B, right? So X transpose B is kind of A times B, right? X transpose is A and X is B. And you can count the number of operations for this. And then Gauss-Jordan elimination is an algorithm for computing a matrix inverse, okay? And if you know how complex that operation is, then you can get an estimate of, you know, in terms of the computational complexity of this part of the equation. And then, after you compute the inverse, this is another matrix. X transpose is another matrix, so it's a matrix times matrix. So again, you can compute, how many number of operations are required. And then finally, the whole thing over here, okay, is a matrix, right? And then Y is a matrix. So matrix times matrix. So again, you can compute the number of multiplications required to compute this. Okay. So doing this exercise is going to be very, 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 very important for you to understand the computational complexity of machine learning algorithms and the strategy to avoid that, complex operation by some simple mathematical tricks. Okay. And as a matter of fact, assignment number 5 is kind of a get around method for that computation. So instead of doing the multiplication sequentially from left to right, here's a little trick, okay? Because the matrix multiplication, the parentheses doesn't really matter, right? So you can kind of rearrange the order of multiplication like this. So we do the X transpose X first and then calculate the inverse, and simultaneously calculate the X transpose Y and then multiply them together, okay? And if you compare the number of operations required for the formula in question 4 and the formula in question 5, you will notice there is quite a bit of difference in terms of the number of operations, okay? Spoiler alert, the conclusion is the formula in the question number 5 is much faster, okay? So you're gonna need to prove that, okay? And then from that, you're going to discuss the complexity of solving a linear system. And then you're going to discuss, some of your creative ideas in terms of how to improve the complexity. So when I say improving complexity, it means reducing the complexity, right? So try to find at least 3 ways. And, the question number 6 and 7 are kind of open questions. So there's no single answer. So that's where your creativity can come in, and everyone is now back to the main room. Well, so I visited a couple of breakout rooms randomly during your conversation, and it seems like on average, people had a chance to at least think about what the answer would be to the question number 4. And that's actually, that's basically what I wanted, to give you a chance to think about this problem. Now, here, I will, show you the answer. Okay, I will show you how we can evaluate the complexity of a matrix multiplication and Gauss-Jordan elimination and so on and so forth. So for matrix multiplication, it's actually fairly simple. So let's consider A, B, C, D multiplied by E, F, G, H, right? So you all know matrix algebra, right? So in order to multiply these two matrices, what you need to do is to multiply the row of the first one with a column of the second one. And that is A times E plus B times G, right? And then we basically do the same thing. We do the same thing for the 4 times. Now, one of the things that we learn way back from matrix algebra or linear algebra class is that in order to be able to do a matrix multiplication, you need to have a condition that the number of columns of the first matrix has to be the same as the number of rows in the second matrix, right? Otherwise, it's not compatible. So if, let's say, A is a matrix that is M by N, then the matrix B needs to be N by, let's say, P, okay? So that's the condition that you want to satisfy. Now, from this, we have 2 by 2 and 2 by 2. And from this, we have seen that the elements of the rows are multiplied together with the elements of the columns of the second matrix. And that's how you compose the first element, right? And then you basically repeat this thing for different combinations of rows and columns, and then you generate the numbers accordingly. That's basically what you need to do. Now, let me try to make it a little bit more generic. So instead of A, B, C, D, and make it childish, let's bring it up to a general arbitrary shaped matrix. So let's say we have m number of rows and we have n number of columns, and multiply by n number of rows and then p number of columns. And as a result of that, what is the size of the matrix? We have m by n, n by p, so n cancels out. So the resultant matrix is going to be m by p. Okay, so I believe you all know this simple matrix algebra rule, right? Now, let's think about the multiplication process. Like I just said, we're multiplying a row with a column to generate an element in the result matrix. So let's say we have a ith row and a jth column, and that becomes the ij element, right, of the result matrix. And when you multiply this ith row with the jth column, if you think about it, we have total n elements. You agree? So we have n elements on the row of the first matrix, and we have n elements on the column of the second matrix. And the multiplication is going to be basically the first element times first element, second element times second element, third element times third element, all the way to nth element times nth element. So total number of multiplication is what? We have total of n multiplication in order to compute the ijth element in the result matrix. Now, if you think about it, instead of ij, let's say kl, okay? And in order to compute the kth element of the result matrix, we need to multiply the kth row with the lth column. And again, there, kth row has n number of elements, and then lth row has n number of elements. And the multiplication of that requires, n number of multiplication. Now, if you think about it, the result matrix is m by p, which means we have m times p elements in total in the result matrix. And in order to compute all this m times p elements For each of the element, we need to do n times of multiplication. So in total, it's going to be n times m times b. Okay? So therefore, the total number of operations required to compute matrix multiplication is m n p. Okay? That's the computational complexity of the matrix multiplication operation. Now, some of you may wonder why we do not count the addition, because we obviously add the numbers, right? So we have, we multiply element by element, but then at the end of the day, we take the summation of, those things. Well, when the computational complexity is concerned, you always kind of, view the problem from an agnostic way, meaning that you basically assume a worst case scenario. Okay, what is the most complex case for this given operation? That's what you're looking for. Now, without talking too much about computer science, multiplication of two scalars is way more complex than the addition of two scalars. Okay, so at the end of the day, numbers in computers are represented as a binary digits, right? So 0, 1, 1, 0, 0, 1, 1, 1, something like that, is how you represent a number inside of computer. And the addition of the binary numbers is pretty simple, right? It's more or less the same as what we do in in a decimal system. It's basically the same rule. And then if you think about it, it's kind of an operation that can be represented as an AND or logic, right? So, for example, you have 1, 1 in binary digits, and then you have 0, 1 in the binary digits. The addition of the two, 1 plus 1 becomes 1, and then you have 1 over here, and then 1 plus 1 becomes 0, and then we have 1 in front. So the result of that, right? Result of that 1, 1 plus 0, 1 is 1, 0, 0. So the addition operation is pretty simple, but if you think about it, the multiplication is not that simple. So multiplication operation, in fact, requires more time. Therefore, when we talk about computational complexity, we talk about only the multiplication, not the addition. Okay. So with that being said, M and P is the computational complexity of computing A times B. Okay. Now, Gaussian elimination, I saw some of the groups who were able to kind of derive their own formula for that. Okay. But here, I'm going to give you a very, very, very simplified description of how that can be computed. Okay. So the answer first. Let's say you have an n by n matrix. D by d matrix. Okay. The answer first, it's O of d cubed. Okay. So the computational complexity of Gauss-Jordan elimination operation is d cubed. Okay, when the matrix dimension is d by d. That's the answer. Now, the reason for that, simply speaking, is for those of you who knows what Gauss-Jordan elimination is, you have, let's say, some arbitrary matrix. Okay, 1, 3, 4. I don't know if this is singular or not, but I'm just going to throw out some numbers here because it doesn't matter. And what you do in Gauss-Jordan elimination is to, select two rows and then basically compute the row-wise multiplication and subtraction. And then by doing that, your goal is to build an identity matrix. Oops, what am I doing? your goal is to build an identity matrix as a result of that row switching. Okay. And simply speaking, okay, I'm not going to go into all the details of Gaussian elimination. Okay. If you want, later on, I can make a separate video about Gaussian elimination, but that's not a point here. In order to compute this, okay, eventually what you're going to do is to switch the first item, the first element, into 1. And then you're going to need to do a series of operations to convert this thing into 0, convert this thing into 0 again, convert this thing into 0 again, convert this thing into 1, convert this thing into 0, and so on and so forth. So we have a total of d times d elements in the result matrix, and those are the ones that you need to convert. Okay. Now, the switch operation, the row switch operation, basically involves a multiplication of a scalar to a row of a matrix. Okay, so each time whenever you convert the element into a target, you're going to need to multiply a scalar value to a row. Okay, and that's the d number of multiplications, because you're going to multiply a scalar, let's call it r, to each of the elements in a row. And then for a d by d matrix, we have d elements in a row, and that's total d number of multiplications. And as a result of that, you end up having d cube of multiplications, okay, in order to compute Gauss-Jordan elimination. Okay. So long story short, if you don't understand what this, how this computational complexity is computed, you don't really need to memorize all this. Okay, you don't really need to understand the derivation of this complexity, or whatever, because that's an information that's available on the internet and you can easily look up. So that's not the point here. The point is, and this is an important point for our course. Okay, the point here is that you have the complexity of m and p, okay, for matrix multiplication, and then you have a complexity of d cube for Gauss-Jordan elimination to get inverse. Now we're going to bring that to the next question. So for matrix multiplication, we saw that the complexity was m and p. And then the Gauss-Jordan elimination, the complexity is d cubed. Okay. By the way, the O here is what is called the big O notation. And that's a notation that computer scientists use as a convention to represent the complexity of a computation. So yeah, that's a convention. So what's important is m and p and d cubed. All right. So question number 4. What is the complexity of computing the solution A, right? And this is something that is really important, and I want you all to kind of think about. First of all, let's say matrix A is, call it n by d, okay? So by convention, n is the number of observations. Okay, and then d is the dimension of the problem. D is the number of parameters. Okay, so X is basically our data table, right? In Apache Spark, we saw data tables, right? So N is the number of rows, D is the number of parameters. Now, when you compute X transpose X, that's like a matrix multiplication between a matrix that's D by N, because it's a transpose, and then a matrix that's N by D. Okay. And let's substitute that into this formula, which will give you the complexity of n d square, right? Because d correspond to m, n correspond to n, and d correspond to p, right? So the complexity of x transpose x is going to be nd squared. Okay, so far so good. Now the result of x transpose x is going to be d by d, right? Because x transpose is d by n, x is n by d. So as a result of x transpose x, you're going to have a d by d matrix. So the complexity of computing the inverse via Gauss-Jordan elimination was d cubed. So the inverse operation is going to be O to O of d cubed. Okay. Now, the next operation is to multiply this inverse. Well, let me erase it a little bit over here. So multiply this inverse with x transpose. So that's a multiplication between a d by d matrix and a d by n matrix. So x transpose x inverse x transpose t, x transpose has a computational complexity of what? nd squared again. Agree? Because m correspond to d over here, d correspond to n over here, p corresponds to large n over here. So that's, again, nd squared. Finally, we need to multiply y. And in order to do that, what do you need? This whole chunk is d by n. So it's a d by n. Oops, let me erase it and then rewrite it. So it's a d by n multiplied by y is n by, let's call it 1, okay? Let's just consider y as a 1 column vector. So in that case, the complexity of this operation is going to be O of nd. Okay, so far so good. So as a whole, if you add them up, what's going to happen is you're going to require a total of d cubed plus, d cubed plus 2 times nd squared plus nd. That's the total number of operations. Okay. Now, when n is large, then it's gonna, the complexity is going to grow as a function of n, and when the dimension is large, also the complexity is going to grow together, right? Now, compare that with the formula in problem 5. Okay. I guess I have 2 more minutes. Let's see if I can finish that in 2 minutes, which is not going to be difficult. So we saw that x transpose x has a complexity of nd squared, right? It's the same thing. And then the inverse of that is x transpose x inverse was a d cubed, right? But then x transpose y, okay, x transpose is a d by n matrix, and then y is an n by 1 matrix. So x transpose y takes nd, okay? And then the multiplication of the whole, I'm just omit that. The multiplication of the whole is going to be multiplication between d by d, right? The left-hand side is a d by d. And then the term on the right is d by 1. So the complexity of the two, the multiplication of the two, is going to be d squared. So as a result of that, we have the same d cubed. Okay, that's something we cannot avoid. But then the other terms, okay, if we compare them together, we have quite a bit of improvement, because what used to be nd squared has become d squared. And when n is really large, that's actually quite a bit of improvement. Okay. So the whole point of this exercise today was to give you some, idea of how the complexity of the algorithms can be improved in the context of big data. And in the next class, what we're going to do is to, first of all, we're going to go over the basic concepts of machine learning, and then we're going to talk about some basics of linear regression. But then we're going to jump on to eventually, supervised learning for big data. Okay, what are the strategies in order to improve the computational complexity of a supervised learning algorithm in big data systems? Okay, and what you saw today is one of the strategies in terms of how we could improve the computational complexity and then make things more efficient. Okay. Again, when you have a small data, it doesn't really matter, right? Which way you compute doesn't really matter. But when you have a large data set, then a small difference is going to create a large, difference in outcome. So thank you very much, guys, and I'll see you on Thursday.